I'm Andrew,
And I'm Ryan.
and we're doing a heated tile floor for our final project. So, for the overview, we're going to find K and emissivity for tile or flooring tile, and then we're going to compare that to an electric heater, central air. So, this is our math that we did. We So really the biggest thing we want to talk about is our Q. We just because we're having an electric coil heat up our tile, we're just doing our voltage times our amperage to have our Q. But with that, because our coils are actually larger than our tile, only about half of that energy goes through the tile. The rest is just going through insulation. So we did do a correcting factor on that. Then with the Rayleigh number, depending on that, define on the value of that defines which equation you use for the Nusselt number. So the Nusselt equation we're using is for a flat plate in the free convection. And so you have the two equations, and depending on the Rayleigh number we find, we'll use a different equation. And this is our math with our numbers in it. So like I said, we have a 1/2 for the correction factor of only about half of that energy actually goes through the tile. And then this is what we found. We found a thermal conductivity of 0.016. We have our T film temperature, and we find our beta, find all of our properties for air, and then we solve for our Rayleigh number, and we do get a value that's smaller than 10 to the 7th. So we use the Nusselt equation of 0.54 times the Rayleigh number raised to the 1/4. And we get 6.94. Our H value equals 6.82. Now, the Rayleigh number is a little bit on the small side, but it is air and free convection, and the Nusselt number comes out as a good value, and our H value comes out as a good value as well. So we thought that it was correct. And then to solve for emissivity, we just used this general heat transfer equation with convection and radiation. We went and put in our values that we had, and we solve for emissivity, and we get 0.716. Experiment, we just use insulation or styrofoam as our insulation, and we cut out grooves so we can set our coil in. And you can see how the coil goes from both sides of the box, and our tile does not. So we had to cut in extra styrofoam blocks to block off two edges, and then for the bottom portion. This is on this portion we put our thermocouple running from the center of the coils, so we have that big open spot, and then we kind of ran over a coil as well, so we could avoid hot and cold spots and get a good average. But we also let everything rise to a steady state, so there should be no. We just were redundant in checking that there were no cold hot spaces, and then we just put a thermocouple above. We tried to get it as close as we could to being above the other thermocouple, and then we used LabVIEW to display the data and verify when we did reach a steady state.
So the results of this lab indicated the conduction equation by getting a thermal conductivity close to an expected value. We looked up different values, specifically under masonry materials in the back of the book, and they all were kind of generally below 1, and so we were happy with our calculated K value of 0.016. The same was done for the emissivity value. We looked up expected values of somewhere around 0.92, and our 0.716 calculated emissivity was not far from that. From this, we have determined that our calculations in these equations were true and accurately represent this environment of heat transfer. The applications for this experiment are many and varied, but in general, cost is a very important one. These results represent costs for heating methods for a 1,000 square foot room with many other assumptions made during the calculation process. However, the assumptions were the same for both methods, so they can be compared. But one should be careful to not associate these actual numbers with a different environment, because for this case they can be used to compare the electrical resistance versus the central air, but in a different situation, all those assumptions that we made, uh, they aren't the same. So just keep in mind that these are for comparative use only. We are happy though that the heating method of our experiment was slightly less than an electric furnace. That would be expected, but we're still happy that it was slightly less. Some improvements we would make for this lab, had we been given everything that we needed to do it 100%, is to make sure that we had a coil or some type of resistance heating that had uniform heat dissipation. At the end of our lab, we turned the heat up all the way, and we noticed that it affected the styrofoam. It made it contract and shrink in certain areas, but it did that more in other areas than some areas. So we're led to believe that maybe the heat dissipation might not be entirely uniform, which would throw off some of our calculations, make them a little less correct. But if you could make sure that that wasn't an issue, then I believe our numbers would be even better than they were. Another thing is that rarely in life do we come across things that are perfect in any way. So it'd be interesting to find the heat that actually goes to the insulation and include that in our main heat transfer equation. If we did that, I'm sure we'd come out with even more correct numbers for our thermal conductivity and emissivity. If you have any questions, please post those in the discussion board and we'll get back to you. Have a good day.